if I the mask while giving you a lecture, it's very hard to talk with mask. It's okay. Okay. After lecture, I'll take on the mask immediately. So I want to give you a clear message. So without mask, I can talk very clearly, but with mask, too hard. Okay, let's get started. Last time we were I think we were here, right? So interrupt processing. So let me recap. We are talking about interrupt and exception in ARM. And interrupt processing sometimes is very difficult because it is not entirely done by software. Right? It is collaboration of hardware and software. So to write assembly program or interrupt service routine, you have to understand what is done by hardware. What is done by hardware, then the rest should be done by software. So that is again collaboration of hardware and software. So if you, the big picture is this, right? CPU, computer is executing your program, hello world program. Then interrupt happens at some point. You move your mouse, your keyboard. Then what you want to do is you want to execute interrupt service routine. That is the final goal, right? You want to execute ISR, then you want to come back. That is the goal. ISR and come back. Right? Then the detailed step. So for transition from this point to ISR execution. That detailed transition is defined by CPU architecture. So CPU vendor, ARM, Intel, x86, RISC-V, they are defining detailed steps to run ISR. That what is happening during this transition. So you have to understand that detailed step. This is a big picture and what is done during this transition. So that slide is talking about the interrupt vector table or exception vector table. So ARM architect defined that IVT, interrupt vector table, exception vector table. So you have to follow the rule. Right? So interrupt happens, then what? Then depending on interrupt type, exception type, right? Normal interrupt, CPU will fetch instruction from location 18. That is defined, right? So you have IVT, interrupt vector table or exception vector table. Right? So location 0, offset. So the starting location is defined by V bar register. You can program V bar register, vector base register. So that means interrupt vector table will start from that location. CPU now know, right? If you program this register. Okay. So from here, so vector, right? reset vector, and second is what? Undefined, right? Undefined exception case. Then CPU will read that instruction. So typically, one instruction is located here, only 4 bytes each in interrupt vector table. 4 bytes each, right? So only one instruction, typically branch, reset, ISR, branch, undefined, undefined ISR, offset 8, what? 8. Software interrupt, SBC, right? Branch, software, interrupt, ISR. So that is defined somewhere in memory, right? So memory, you have, for example, SBC, ISR. Okay, so you are branching to here. You have undefined interrupt, exception handler. So you are branching here. So actually that is located in memory, right? IVT, location 0. So IVT, you are branching here. Okay. the thing you want to do is, so what should happen? What should happen during this transition? In addition to this IBT, you want to preserve the state of this your application program. You have to preserve that state. What do you mean by state? The registers, right? The general purpose register R02, R15, and CPSR, that state. Then when you come back, you resume from that interrupted state. When you come back, you keep executing from interrupted state. That is what you want to do. Right? So then the question is how to preserve the state. How to preserve the state. That is collaboration of hardware and software. Some is done by hardware, and the rest should be done by software. So hardware is doing what operation? Okay. Hardware is doing that operation. Okay. The first bullet. So CPSR. So hardware is trying to do very minimal amount of operation to preserve the state, very minimum, and that is essential amount of work. If hardware is not doing that operation, we have some problem. We have correct this problem. That is why hardware is doing that operation. Okay? So first thing, hardware is doing CPSR, current program status register. CPSR will be saved in SPSR. The first bullet. Okay? The reason why we save this CPSR because we are going to change some field in CPSR later on. If you look at that third, fourth, those bullets. So mode bit in CPSR and interrupt mask that bit that will be changed by hardware. Right? So before you change, better update, right? better backup, right? So that is done, and let me write down. CPSR mode bit will be changed to what? IRQ mode or FIQ mode or supervisor mode or undefined mode, depending on interrupt or exception type. That will be changed, right? IRQ mode, FIQ mode, and so on, depending on exception or interrupt type. Okay? Then CPSR I bit. CPSR I bit will be set to 1, meaning that I bit, interrupt masking bit. That means CPU will not take interrupt while processing current interrupt. Okay, I'm busy, right? I'm busy processing interrupt. I'm not going to take additional interrupt. That is the meaning of this I bit. Interrupt masking bit. Right? You have CPU. CPU, you are taking IRQ or FIQ. That is physical line, really. The fine wire coming from some IO device like keyboard. So FIQ, let's say it is coming from time. It is connected, physically connected. That is really fine wire 전선 in Korea, right? Korea 전선, very fine. So CPSR I bit to 1. Then even though you raise this line like this, okay, interrupt is generated, CPU will ignore that interrupt because I'm busy, right? I'm busy processing interrupt now. Okay. So again, this one is updated CPSR. That is why CPSR will be backed up before update. So that should be done by hardware. And the second bullet, link register. Link register should be updated with the return location. Return location is return location. Only CPU knows that return location, right? Because interrupt happens asynchronously. You never know when it would happen, right? When CPU, computer does not know when you type, when you type the keyboard and you move your mouse, computer does not know, right? Asynchronous event. Interrupt can happen here, don't know, right? Asynchronous. That is why only hardware should update link register with the return location. That return location. Okay. That's it, right? That is done by hardware. That should be done by hardware. So hardware is doing this minimal amount of work and essential, very essential amount of work. If hardware is not doing this operation, we have a problem. Correct this problem. And what else? What else should be done? Okay, to preserve the state. When you enter into interrupt service routine, you are doing push operation. Push CPU context. It's a general purpose register. Hardware already backed up CPSR. Right? So you don't have to back up this CPSR. Okay? This general purpose register should be pushed because you are going to use in ISR, okay, main routine. You are going to use general purpose registers. Before that, you have to back up to stack in memory. And at the end, pop. You are done executing your ISR, right? So you have to back up. Then return. Then return to the place. Okay. So when you return, you have to do opposite operation. This opposite, right? This SPSR to what is that? The second bullet, return from interrupt. SPSR to CPSR, opposite. To CPSR to restore the state. Restore, right? To restore the state. And link register, right? You updated link register. So program counter should be updated with that. So that is opposite operation. Okay. To do that operation, you have to use special instruction, not return instruction, right? In ARM, you have to use move PCLR, like this instruction. But this instruction is not enough. If you look at this, move, then LR will be written to program counter. That's it, right? So you are doing this operation, not this operation. Right? So to do these two operations, you have to put what? S suffix. So you have to be careful about the meaning of this S suffix. Okay? In arithmetic operation, think about R1, R2, R3. Don't be confused. This one is a little bit confusing point. Right? This operation, you are doing simple addition. R1, R2, R3. Okay? But if you have S, the same S, then what? What is done? Flags, right? NGCB. Flags will be updated. NGCB in CPSR. CPSR update. Right? So that is the meaning of this S. But the meaning of this S is different. You are not doing CPSR update, not only CPSR, because you are doing whole CPSR update. So inside CPSR you have NGCB and some other different fields. So you not only update NGCB, but NGCB is coming from this SPSR. So the rule is this: if the destination register is program counter, that is the rule. If the destination is program counter and you have S, then CPU is doing this operation. That is the rule, right? Think about that. Program counter update is a super dangerous operation. PC update. When do you update program counter? Think about that. When do you update? Yes, when you make a function call, right? When you make a function call and when you return from function, right? You are updating, right? So and also this case, when you process interrupt is generated, then program counter will be updated. PC, I didn't write PC. PC will be updated with here. Not only this, the last step is program counter. Program counter will be updated to one of these IBT, right? One of these location. Depending on interrupt type, exception type. Right? Location 0, location 4, location 8. Okay. So program counter is updated to execute interrupt. And when you return back, you have to update program counter. Right? So function call, and interrupt, exception processing. Then you update program counter. So again, the rule: if the destination is PC, then S, then your CPU will do CPSR update from SPSR. So you can use many different instructions. So many different, not only this, right? This is not the only instruction. You can use, for example, same addition instruction. Add PC, LR, then symbol 0. Constant 0. Then you can put S. Same operation, right? Addition, right? Addition, update program counter, but you have S. That means not this, right? Not this NGC update. You are doing this one. Okay? What else? You can do this, right? So S, PC, LR, constant 0. Subtraction, but 0. So you are updating PC, you have S. That is what you are doing. CPU will do that operation. So you can use, you can have many different options to return from exception. Right? This one, some other instruction, probably. Some other instructions, if you want. Okay, any questions so far? Yep.
CPSR 같은 경우에는 IBS만 인터럽트가 하더라도 기존에 있던 NGCV가 그대로 남아 있는 상태로 인터럽트가 진행되면 기존에 있던 것들을 쓸 수 있다는.
Yes. So here, right? You want to preserve the state of your application program. You got interrupted here, right? At this point, what is NGCV in CPSR? You want to preserve that state and resume from that state.
어차피 CPSR은 ISR로 서비스 팀해가지고 CPSR을 쓰잖아요.
Yes. You are going to update NGCV probably. 네. NGCV flags.
초기화를 하지 않고 그냥 넘어간다는 얘기 자체가 그 전에 있던 상태들이 유지된다는 게.
Here you have still CPSR register, right? That's CPSR and NGCV. Yes, very good question. You have CPSR, same CPSR, right? You backed up here, but CPSR is still, right? Still, the data is still remaining, right? So CPSR, NGCV. So the two you use is NGCV, okay, fresh. Probably you want to use, compare CMP, R0, R1, then you are completely updating NGCV. Before you use NGCV, you have to use, right? So in interrupt service routine, probably you want to do, I don't know, R0 is equal to R1, then you do addition, otherwise subtraction, right? So to compare, then you use compare instruction. That will update the NGCV. So from this updated NGCV, you can do some operation. Even though that information is still remaining here, you can fresh start with that instruction. That is normal, typical usage. So you don't want to use NGCV in application program in ISR. That is not making sense. Okay, any other questions? Yes. 뭐라고 그랬지 안 들려. Oh yes. So if you check out this one, register table. So almost every operating mode, almost 9 different operating modes, right? From user mode, system, hypervisor, 1, 2, 3, 4, 5, 6, 7, 8, 9. And each operating mode, for example, IRQ mode. IRQ mode, you have separate R13 step pointer and link register. Separate, physically separate. Physically, right? FIQ mode, you have a physically separate step pointer and link register. R13 and R14. And especially in FIQ, not only R13, 14, but R82, R12, 5 additional separate, physically separate registers. Dedicated only for FIQ. So almost every supervisor mode, you have R13, 14. Abort mode, separate, undefined, separate. So you are not using this SPLR. When you switch to supervisor mode, you are accessing both registers. You still use programming, right? In assembly programming, you still, right? Let's say SVC instruction. You just executed software interrupt instruction. Then you branch it to eventually branch it to ISR. Then you are in supervisor mode. The supervisor mode. Then inside this code, you can probably write addition stack pointer. Okay, you want to adjust stack pointer. -8, for example. You want to adjust the stack pointer. If you use SP, then you are accessing what? You are accessing that stack pointer. This one. Not user mode stack pointer. So here in user mode, you can write this, addition SP, same code, right? -8. You are in user mode. That stack pointer, we are talking about that step pointer in user mode. In supervisor mode, this code, we are talking about separate that supervisor, that step pointer. So the thing is, when you turn on your the system JetBoot, what you have to do is you have to initialize that step pointer. That is typical procedure. Okay, we have to, because we are going to do everything. There is no operating system. We are going to create operating system, okay, later on. Okay. Then at the booting sequence, you have to switch. Okay, when you boot, then CPU will go to supervisor mode at the beginning. We have okay, here, right? So reset, exception type. Depending on exception type, okay, you reset, you reboot or turn on JetBoot, then CPU will go to supervisor mode. Okay. And in supervisor mode, you have all the power to do anything you want. You have enough privilege to touch every register, all the register, system register, not only general purpose, but VBAR, like vector base, for example. Anything you can touch, right? And also you can change operating mode, CPSR, MBIT, okay? using CPS instruction, change process state. Okay? For example, you can do I think 13. 13 is supervisor mode. Some other checkout in some other encoding. By using CPS instruction, you can change operating mode. So what do you want to do in the booting sequence? From supervisor mode, probably you can switch to abort mode and initialize step pointer. Then abort mode, you can switch to undefined mode and initialize step pointer. Separate the step. That is a standard procedure. Each operating mode you reserve separate step. For example, 1 kilobyte step. For supervisor mode, another 1 kilobyte step. For undefined mode, another 1 kilobyte step. For IRQ mode, another 1 kilobyte. For FIQ and so on. That is a standard booting procedure. You have to initialize step pointer at least. Step pointer. Any other questions? Okay, let's move on. Okay, so returning from exception, this one. Okay, 종욱. Yeah. Okay, so before we talk about that, I have to explain this one. This one first. 지성? Yeah, that is a little nasty mechanism, nasty feature. You have to follow. You have to follow that rule. No choice, because ARM hardware was designed that way. What does that mean? When you return from exception, you have to do some little adjustment of link register, the return location. Right? So in case of software interrupt execution, you don't have to adjust return location in SVC, right? So when you return, you don't have to change this one. Return location is saved by hardware. But in case of SVC, you don't have to change this one. Okay? You can just use move SE instruction. But in case of IRQ, hardware interrupt coming in from IRQ pin, CPU, IRQ, FIQ. So interrupt happened through this pin. Okay. Then before you return, you have to do subtraction, -4. So the thing you have to do is, so ISR, then when you return, you have to write this code. For example, SUPS. Okay, that's the first example. SUPS. Destination is program counter, and LR you are doing -4. You have to do this operation, then update program counter. Okay, destination is PC. Then you have S suffix. That means SPSR is copied to DPSR. Okay, then the question is why? Why do you have to do this -4? That is nasty. Okay, uncomfortable to software programmer. But if you understand hardware mechanism, it is going to be not that nasty. Why do you think so? Why do you think you have to adjust this link register? But the thing is, ARM architecture reference manual does not say anything. ARM specification just say, okay, before you return, you have to do -4. That's it. then there's a story behind. What do you think the story behind? Can you open the door, please? What do you think the behind the story? Story behind. If you remember computer architecture class, right? The five-stage pipeline design. Think about that how interrupt is processed internally inside the CPU. Let me draw pipeline. Think about the five-stage pipeline. You have instruction fetch, instruction decoding, and execution. E, memory access, VM, and write back. That is five-stage pipeline. Fetch, decoding, execution, memory access, write back. Fetch, decoding, interpret, machine code. Then actual execution, ALU operation, and memory access, depending on instruction time. Then write back. And fetch, decoding, execution, memory access. And clock is running like this. So the beauty of pipelining every clock cycle, if you look at this specific clock cycle, at this clock cycle, one instruction is done. Let's say addition, R1, R2, R3. Right? So addition instruction is done. Right? And second, let's say LDR, memory access, R5 from R1. Okay? Then next instruction, next clock cycle, load instruction is done. Okay? Third instruction, let's say subtraction, R5, R6, R2. That instruction. Then let's say IRQ. IRQ happened like this. IRQ line. Interrupt. You press the button. You have keyboard. Keyboard here. You press the button. Keyboard button. So line got raised. Interrupt is generated. Then CPU now recognize because line got asserted. Right? CPU recognize. Okay. At the rising edge of the clock. Okay, that is one. So something happened, interrupt happened. Then what should I do? CPU. Think about your hardware design, internal hardware design. Then the detailed implementation is really depending on that microarchitecture, but mostly hardware design is done like this. Hardware CPU will finish executing the instruction in execution stage. If the instruction is in execution stage, when interrupt happens, then I'm going to finish executing that instruction. I'm going to finish that instruction to the end. And then I'm going to stop here. Okay, finish that instruction, then it is done. Then resume from when you return. Okay, resume, right? You have to resume. I'm going to resume from that point. You have to think about this pipeline execution. Then what is happening? Okay, CPU keeps executing to the end, but you have to think about program counter. How program counter is changed. Let's say this instruction is located at 100. Okay, next instruction, each instruction is 4 bytes in size, right? So 104. Next one, 108. And this one is the return location, right? That return location. Okay. Return location. But the problem is, program counter, right? You have PC register here inside. Program counter register R15. Think about that, how that program counter is changing. Here you have PC, PC 100. You read that instruction. 100, that instruction. That instruction is passed to decoding logic and interpret. Now, when you interpret, then CPU at this point in time, CPU interpret that machine code, addition machine code, at the same time, read next instruction. From program counter will be 104. From 104 next location. New instruction, load instruction will be fetched. Okay. So now at this point, right now next class CPU. That is CPU status. CPU in execution stage, CPU is doing addition operation. Okay. And decoding stage, CPU is interpreting that machine code. At the same time, in patch stage, CPU is reading new machine code, which is subtraction. So now 108. So 108, new instruction. New instruction is patched inside the CPU from to CPU. So then interrupt is generated at this point. Then ARM architect decided to save that information, program counter information to link register. Because program counter already got changed to 108. You are supposed to save that 104, but that information is already gone at this point in time. Interrupt got generated. Right? So I'm going to save the program counter at this specific point in time. So at this point, program counter already 108. So instead of doing subtraction by hardware is not doing subtraction because that means what? That means you need to add additional hardware to do subtraction. If we are happy if CPU simply say that 104, okay, it is not a big deal, 108, but if CPU is doing adder, right? Separate adder. So you have program counter, then -4. So you get 104. So that information is saved in LR. Then we are happy. We don't have to do any adjustment, right? When you return, you can simply use move PC LR. So then you are happy, right? So no adjustment. Okay? But CPU designer ARM decided to save that information. To save what? To save hardware resource. I don't want to invest hardware resource. If you add that hardware, then that is what? CPU is going to be expensive. Okay. ARM has a little bit long history, more than 30 years old history. ARM was invented as embedded CPU processor company. Embedded company. So the CPU integrated in the home appliances. Okay. So mobile device. Not at that time mobile device, but it's supposed to be very cheap, only 1 cent or 2 cents CPU price. But if you add adder, then the price is going to be increased. They don't want to do that because they were originally embedded system company. Okay. Nowadays, that is not a big deal. Like these days, 1 billion transistors are integrated. 1 billion Chibok transistors are integrated in smartphone application processor. Right? So these days, this is not a big deal. Right? Adding one simple adder is almost nothing. It costs nothing. Right? So these days, this is not a problem. But because of that historical reason, ARM, version 7, we are using Cortex A9, right? That is based on ARM version 7 architecture. They still use that the mechanism LR adjustment. But if you take a look at this ARM version 8, next generation, version 8, 64-bit, 64-bit processor, that mechanism is gone. Okay? So you can simply use move S, PC, LR. They invested that additional hardware for easy programming. So in version 8, wholly new architecture, because that was introduced a little 10 years ago, 2010, 2011, around that time frame. At that time, there are abundant amount of transistors, abundant amount of audio resources you can use. So adding just one adder is not simple, very small, tiny, like nothing. So there is a history. There is a history. When you get interrupted, program counter got already changed, and ARM architect decided to save that information to link register. So depending on interrupt or exception types, you have to do that adjustment. Okay. Again, that is not happy, right? We are not that happy. Okay. It sounds very strange, why? CPU saved return location to LR, then at the end, additional adjustment, it is not happy, right? But we have to follow that rule. Any question? But at the end, all you have to do is, at the end, you have to do, when you write assembly program, at the end, when you return, you have to use subtraction, -4. If the exception type is hard interrupt or fast interrupt. IRQ, FRQ case, -4. Okay. And software interrupt case, you don't have to do any adjustment. No adjustment, right? And undefined instruction, no adjustment. Okay. And this abort, -4. Prefetch abort, data abort, -8. So far so good. Okay, so it's the one, and then let's talk about nested interrupt. Nested interrupt. This nested interrupt is making things a little bit complicated. Like nested function call. When you make a function call inside the function, you want to call another function. Get foo. Call for another function inside the function, you can call another function, nested function call. So in case of nested function call, what do you have to do? Let me draw. It is very similar, right? So interrupt processing is similar to function call, except you have to save CPSR information, and also some adjustment this stuff. And nested interrupt processing is also similar to nested function call. We have similar issue. Okay? So what issue? So think about nested function call. You have main, then you are calling some foo, procedure 1. Okay? Procedure 1. Then procedure 1 is calling procedure 2, that is calling procedure 3, and so on. So, then you are supposed to return back to the call log. We are using BL instruction, branch and leave, to make a function called P1. And here you are calling another function called P2, right? Procedure 2. Then at this point, you are supposed to do this and return back. And here the L, you are calling P3. That is execution flow. So what issue you have if you write assembly program? When you make a function call using BL, then what is done by hardware? Two things. Two things. First one, PC. PC will be updated with P1, the label. Right? The label is what? Label is a location of the first instruction. We have many different instructions. Addition, subtraction, many different instructions. Location of that first instruction. That is the label P1. So P1 is updated to PC. Okay. Second operation, what? Link register. Return occasion, right? It's a return occasion. A. It's a return occasion should be saved in link register. These two operations are done by hardware. Same thing is done, right? Same thing is done. If you don't do anything, then simply use BL. Then first operation, while making transition, right? PC will be updated with P2, the location of the first instruction. And then link register, let's say location is B. You see the problem then? What is the problem? You don't do anything, simply use BL, then link register. Link register will be updated with B. So you can return back to this place, but if you use move PC L R, then you can return back to this location. Right? So here you are using same rule, move PC L R. But at this point, right? LR contains A. Sorry, P. Not A, because that guy is updating. This guy is updating link register with the new information. So if you execute this, then you are going back to this location, not this location. Okay. So what do you have to do then? Before you make a function call, you have to push link register. Push link register to stack. Okay, and pop. Push and pop. Because that guy is updating link register. So we have a same issue in interrupt processing. Okay, same issue, right? So now, it is not function. It is not function. It is interrupt. Now, interrupt is generated. Interrupt, and another interrupt is generated. Let's say so interrupt the ISR and another ISR. So this one let's say keyboard ISR, this one mouse. ISR for mouse. Okay. And tradition is interrupt is generated. The thing is, you see what you see is okay when you make this transition, CPSR, right? CPSR I bit will be set to 1 by hardware. Hardware will set this I bit to 1. That means what? Interrupt will not be taken during this interrupt processing. Interrupt will not be taken by CPU. CPU is blocking, right? Interrupt, but you can enable that interrupt using software. Even though hardware blocks it, software, okay, in ISR, okay, I'm going to allow to accept additional interrupt using CPS, change processor state, right? CPS instruction, interrupt enable. Okay, I want to enable I bit. You can use this instruction to enable interrupt. The rationale is okay. I'm processing keyboard interrupt, but what if higher priority interrupt is generated. This one is lower priority and mouse is higher priority. Then even though I'm doing some interrupt processing, I need to take that interrupt because that is more higher priority. That is the rationale. Okay? So you enable the interrupt and mouse interrupt is generated. Then no choice, you have to pass interrupt. Right? Then the problem is during this transition, right? What is happening? Okay, can you see? SPSR, right? That SPSR register will be updated. And here, SPSR, right? Same SPSR will be updated. You are overwriting SPSR. And link register also, link register will be overwritten by that during this process. That means what? That means you have to push. You have to back up, right? You have to back up SPSR. Back up these two registers to the stack. Right, like this. Before enabling interrupt, you have to push SPSR LR, okay, like this. Okay, and at the end you have to pop. Push and pop. Okay, does it make sense? Any question about this? Okay, then some detail. Push SPSR, then probably you have to use MRS instruction. Push for push operation. Push SPSR. Probably I don't know if that is allowed. In pseudocode is allowed, but in real instruction you have to use MRS. Okay. R0 for example, SPSR. Okay. Copy that SPSR status register to general purpose register. Okay. R0, then push, actual push. R0 like this. Push. You have to use these two instructions to push. Okay, and then the next instruction, push LR. And let me show you. That is too boring. Okay, only lecture is too boring, right? So let me show you this. You can download. You can download what? 1, 2, 3, 4. This one. Software interrupt and undefined. That is an example of nested interrupt and exception process. So software interrupt generation, and inside software interrupt generation, inside software processing, interrupt processing, I'm generating undefined exception. So it's somewhat nested, right? Or opposite. Undefined instruction first, then software interrupt here. So you can download. Let me check out the code. Oh, here. So main, right? Main. There is a code inside the main user program. I'm generating undefined instruction exception. So there is no operation. I deliberately put this code. This is not defined by architect. This is not instruction, not legal instruction. So CPU try to patch and execute this instruction, then undefined exception will be generated. Okay, and undefined exception I left only 2. Okay, undefined exception CPU will change program counter to this. So CPU will execute this, handler CST undefined. Scroll it down. undefined. Okay. Then inside here, you are generating software interrupt. So nested, right? So that if you execute this, then what? CPU will execute this branch instruction from interrupt vector table. Okay. So that is, scroll it down, CSD, software interrupt processing. So inside here, we are just toggling LED for demonstration purpose. Okay. And before that, you are doing some, push operation here. Undefined interrupt processing, we are doing push operation with SRS. We haven't studied SRS, but I have a slide. So push some state and general purpose register. Okay. So what is SRS? Let me explain. Okay, that is SRS. Okay. Some shortcut instead. Okay, so instead of using these two instructions, instead of using push SPSR, these two, ARM is providing shortcut, one simple instruction to do these two pushes. Okay, one shortcut, simple shortcut. That is called SRS. SRS instruction. What does that stand for? Save return state. Save return state. Okay. Okay, so save return state, that instruction, that is the format. SRS, then suffix, full descending state. Remember, when we discuss memory access instruction, stack operation, full descending, that is default state. Right? Full descending, we assume stack is full. Memory, right? Then location 0, address is incrementing like this, and that is stack. Let's say stack for IR2 mode, interrupt, no more interrupt. Then full descending means assume that stack pointer is pointing that location, and the location is already filled with some information. That is full stack. Full. The location is already full, already occupied by data. And descending. Like descending means before you push additional data, you have to decrement. Decrement, full descending, right? Descending. Decrement is stack pointer. Because it is already filled with data. So before you push, you have to decrement, then push right. Full descend, FD. So the meaning SRS, save return state, and the mode, right? Full descending. That is typically used. So you don't have to worry about other mode. Just use full descending. You can use full ascending, empty descending. This, one of these four choices, but that is typically used. So SRS FD. That means what? That means you are saving. If you execute that instruction, you are saving that animation. SRS, SPSR, then LR register into the stack. One instruction is doing that two push operations. So that is shortcut. You can just use SRS. Okay. When you return, you can okay, here you have to specify operating mode. In this case, I want to push these two registers, SPSR, LR, into IRQ mode stack. So one two means IRQ mode. IRQ mode stack, FIQ mode stack, undefined mode stack, and so on. So you can specify which stack you want to push. And RFE, return from exception, that is also a shortcut. You can use RFE, return from exception, and full descent from the stack. Then you are just reading from its memory. Opposite operation. So like this. Okay. You are reading from memory. Okay. You are reading from memory, then update. Update what? CPSR, then program counter. PC, right? LR will be updated to program counter. You are returning, right? You are returning from exception, right? Returning. So that means program counter should be updated. PC returning, right? PC should be updated. So in the example code, okay. So I used the first, look at this, undefined, right? The user program, I change it to user mode. Okay, then undefined instruction exception. So then eventually you will execute this handler. Okay, here SRS, FD, I save what? Link register. Link register and SPSR. Okay, and next instruction is saving what? Saving these general purpose registers, because you know in ISR body you are doing some operation typically. You are using R0 to R12 to do some operation inside ISR. Right? Then at the end, opposite operation. You push it, I pop. Okay, you push it here, I pop. Okay, and then for illustration purpose, software interrupt nested, right? Interrupt. So eventually you will execute that code. Okay, so here push operation, then pop operation. Push and pop, right? And some code you should execute. Right? Okay, let me show you a demo. Okay, to only look at listen to lecture. Debug undefined session. Okay. Okay, now 5. Okay, so interrupt vector table. Okay, set V bar register. That is a system register. Okay. We are updating system register to use our own interrupt vector table. That is our own, right? My vector table. We want to use that. Right? So then here I'm changing processor state to supervisor mode. To what? To do what? To set up stack pointer. So if you scroll it down, I reserved, right? Okay, SVC stack 1 kilobyte supervisor mode stack and 1 kilobyte for undefined mode stack. I reserved this stack. Okay, then booting sequence, right? Standard booting sequence. Change state operating mode to supervisor mode. Then set up stack pointer. Okay, and change to undefined mode because we are going to use undefined and supervisor mode in this demo. Okay, and set stack pointer. And change to user mode. Now CPU in user mode execute some code. Some code is this forever loop. Okay. So no operation, some illegal instruction. So undefined instruction. So CPU will generate undefined exception. Undefined instruction exception. Okay. So let me execute it. 5, 5, 5. Let me execute it. Change process state. So you can check out this CPSR, right? So now CPS 10, right? So mode bit 10 in hex. Okay, so that is a user mode. Okay. Then if I press F5, then next instruction is undefined. So CPU will refer to this vector table and read this second instruction from vector table. Okay, then a branch instruction. So SRS. You are saving what? You are saving SPSR and return location. So check out just for illustration purpose, right? So let me show you. Let me show you that what is a stack pointer. So 1 to 1. So that location. 1 to 20. 1 to 20. 10 to 20. Then full descending, right? The first time. So stack pointer is 10, 2, 1, 0, 1, 0, 1, 1, 2, 2, 2, 0. So stack pointer full descending, right? Full descending. So that will be decremented. 1, 2. Next location is 1, 2, 0, 1, C. So for stack pointer is this one. So let's say this location, then decrementing, right? 1, 2, 1, C. 1, 2, 1, 8. Next location. So SPSR and LR will be saved at those locations, right? So let me show you. So somewhere here, right? Let me make it big. Somewhere here. And the information you are saving, undefined mode, right? So here you have undefined mode. Okay, undefined mode, you have SPSR and link register. This data. Undefined mode registers. Okay, so that information will be saved. Okay, so SPSR, LR will be saved somewhere here, I think. Somewhere here. Let me press F5. See the information. This one is SPSR, and this one is, I think, link register information, LR. Okay, so next instruction. Next instruction is pushing R0 to R12, right, to the stack. So R0 to this one, R0 to R12 to the stack, this whole information. So if I press, then those area will be populated with R0 to R12. I press F5. See? Right. Then now software interrupt. Okay, software interrupt instruction. So F5 nested, right? You are here. Undefined instruction. Now SPC. SVC, so it's nested, right? Exception. So F5. Then refer to interrupt vector table. So reading from this location, which is branch. So 5. So here, software interrupt service handler. So undefined handler, SVC handler. Okay. So you are doing, same push operation. I don't have to show, right? It's memory dump, right? So F5, 5. Now, LED. For illustration purpose, LED toggle. LED. LED. Then return. Okay, return. So we are here. We are about to return back to this handler. Right? So pop operation and return from exception. You are popping SPSR and link register. Okay. You are return back to, look at this. You return back to here. Next instruction. Okay. So you return back to SBC, right below, next instruction. So another return, you are popping from undefined state. Undefined state, you push it to undefined mode, right? So 5, return from that. So you go back to here. So undefined instruction. So next code. So forever loop, right? So you keep generating undefined exception, software interrupt, right? So toggle LED. You can do experiment. Right? Return, forever loop, right? So now another undefined exception. So, any question about this? Everything is clear? Why so silent? Silence is not good sign. Okay, any question? Anything is okay, right? So I don't have enough time to talk about new stuff that is about interrupt controller. That is super important stuff. We are going to talk from next class. So I don't want to start a new topic today. So what else? Did I miss anything? Oh, one more thing. Okay, that is, I forgot. So here, depending on exception type, right? Depending on exception type, for example, IRQ, if no more interrupt generated, then CPU, no more interrupt, IRQ generated, CPU will block interrupt, right? Disabling is not taking interrupt by setting IB to 1. What if you do this? There is IRQ, no more interrupt. What if you execute here? What if you execute software interrupt instruction? So you have IB set to 1, meaning interrupt will be blocked. And what if you execute SVC instruction? Inside ISR, that interrupt will be taken or not taken? IB set to 1. What do you think? That software interrupt will be taken or ignored? 지성, no more interrupt, right? IRQ, no more interrupt is taken. No more interrupt is taken, IRQ interrupt. So that means the CPU block processing, CPU blocks additional interrupt by setting IB to 1. But now you put SBC instruction inside ISI handler, so service interrupt handler. Then the question is that interrupt, software interrupt, will it taken or not taken? Not taken because you blocked it. IB to 1. Parts of here. Okay. Okay, Himi, what do you think? State interrupt will be taken, software interrupt. Software interrupt. Why taken? Why CPU will take that interrupt, software interrupt, even though I bit is set to 1. It will be taken. Why? Because it is not, hardware interrupt. It is not IRQ interrupt. Right? This I bit is blocking only IRQ interrupt coming in from outside. Software interrupt, it has nothing to do with I bit. Software interrupt, right? It has nothing to do with this I blocking. So don't be confused, right? Don't be confused with this table. Even though it's I bit, F bit setting, I bit means it is blocking interrupt coming in from this outside world IRQ. This interrupt will be blocked by that bit. And F bit, CPSR F bit. F bit is influencing that into only that into. It has nothing to do with software interrupt as we see. Nothing to do with it. So think about that in ISR. You want to what is the purpose of using software interrupt? So typical usage you want to do that is used to implement system call. System call, right? Inside ISR, you want to do open file close system call, right? That should be taken. That should be handled. So that is one, right? Okay, that's it. That's it for today. I'll see you next time. Okay.